All right, here we have a car entering a horizontal flat road, curved roadbed of radius of um, 80 meters. So basically, we have a car going around a curve like this, okay, on a flat road. So here's the car from the bird's eye view, okay, going around like this. And what's keeping the car in the circular motion or circular path is the frictional force between the tires and the road, okay? That's pointing in towards the center of the circle. So if you were to look at from the front view, right? So here, the front view is here's my Hummer, right? And I have my 50 caliber machine gun mount up there. Yeah, right. So what's happening? Well, there are three forces acting on this. Those three forces are as follows, right? We have obviously Fg is the obvious force, that's the weight of the car, and the normal force from the ground to the car, right? And then we have one force that's very, very important, and that is the frictional force that is keeping this car in a circular path, right? So if we were to look at the vertical forces, the vertical forces is pretty easy. We all know that sum of all forces in y is equal to MAY, and AY is zero because it's not going to be going off the road or it's not going to go through the road, right? And sum of all forces in y is equal to F normal plus Fg, right? Now, so 0 is equal to, I'm going to consider up positive, so F normal is positive minus Fg. Therefore, F normal is equal to Fg, which is equal to just mg. Okay? Now let's take a look at the horizontal. Sum of all forces in the x direction, if you look at it, is mac, because acceleration in the x direction is the centripetal acceleration, right? And the direction of AC is that way, and that's the positive direction. And there's only one force in the x direction, and that is the frictional force, okay? And since they're going in the same direction for AC, they're the same direction for both of them, right? And AC is positive. MAC then is equal to F friction. So we know mv squared over r is equal to mu times the F normal. But we know the F normal is equal to mg, right? So if we substitute that in, we got mv squared over r is equal to mu times mg. So notice how the mass of the car drops out and cancels out, okay? So we're looking for the minimum speed, so we're looking for v, right? So v is equal to mu times g times r square rooted, all right? So if you plug in the right values, the v is equal to then square root of mu, which happens to be 0.35, times g, which is 9.8, times r, which happens to be 80 meters. And if you work that out, I think you get something like 16.6 meters per second, right? Now that's okay. What does that mean? Well, that's around 60 kilometers per hour, right? For those of you who are Europeans and Canadians, you drive in kilometers per hour. And if you're American, that's approximately 37 miles per hour. Okay, so there you go. All right, now comes next. Well, a car rounding 200-meter radius curve that is built on 35-degree banked incline so that less friction will be needed to negotiate turn safely without sliding. All right, so I think first thing is first that we should actually draw out the embankment. So this is like if you're looking at the car coming at you, right? If you cut away the embankment, right? If you cut that embankment away and you look at the car coming straight at you, right, you will see this. Do not rotate the XY coordinate system, okay? So you keep your XY coordinate system just like the way we always do for other things, so that here's your X, here's your Y. This is not an inclined plane. This is actually banked curve. So if you had your car right here, okay, okay, so here's the real Hummer, right, Humvee, right, it's a lot flatter, okay, and if you were to draw force diagram on this, John, you have FG going down like this, okay, and you have a normal force that is going like this perpendicular to the embankment. And notice the F normal is actually bigger than your FG, because this angle theta, this angle theta right here, if you were to look at it, is same angle as my this angle and this angle are same, and this angle and this angle is the same, right? Because if this is the complementary angle of this angle to make it 90, since this is here is already 90, and this is the same complementary angle as that, which is theta, right? So this is theta, and vertical angles are congruent, so this is also theta. So this F normal can be broken up into F normal y, right? So this is F normal y, and F normal x is basically this, right? This F normal x is the centripetal force acting in towards the center of the circle, because this thing is like going like that, you know? So if it's going like that, it is pointing in towards the center, all right? So if we look at um, just this without friction, let's say this thing is going without friction, and let's see what the safe speed of this car should be without friction. Then, once we realize what the safe speed is, we can actually compare that with the actual speed that it is traveling. So if it's going more than the safe speed, then friction has to be playing a role. If it's less than the safe speed, friction also has to play a role. But if you're going at the exactly correct safe speed, you don't need friction at all. All right, so we really cannot draw the frictional force vector onto this yet. All right. All right then. Let's take a look at what's going on vertically first. Right. So if we were to look at sum of all forces in the y direction, right, it is equal to MAY. But in the y direction, we're not really having this thing going this way or going that way. There's no acceleration in the y direction, so you know AY is 0. In the y direction, sum of all forces in y, there are two forces, Fn in y direction plus Fg. Now we're going to say, let's just say up direction is positive. Then 0 is equal to, because this is 0, Fny is positive, then Fg has to be negative. But what is Fny? Well, Fny is the adjacent component of my Fn, because this is the hypotenuse, this is the adjacent, so we have to use cosine. So Fny is equal to Fn, right, times cosine of theta. Therefore, if we bring this to the other side, we get positive Fg is equal to Fn cosine theta. So if we solve for Fn, right, Fn is equal to then Fg over cosine theta. And that is exactly same as m times g over cosine theta. Well, that's good to know, right? Because if we were to take a look at the x direction, sum of all forces in the x direction is equal to MAC, because that's the direction of my AC, right? Because it's going in a circular motion. And sum of all forces in the x direction, there's only one force in the x direction, and that is the Fnx. And Fnx is equal to the opposite of my Fn, theta, right? So it is Fn sine theta, okay? So I can replace that with Fn sine theta. So MAC, which is in that direction, and Fnx is also in that direction. So they're both positives. And MAC is V squared over R, and Fnx is Fn sine theta. But this Fn and this Fn are same Fn's. So if I were to substitute this into here, I have mv squared over r is equal to, right? I'm going to just put a different color for now. Mg over cosine theta times sine theta. So this is really, masses can cancel out, so it doesn't matter how massive the car is. It will all behave the same way. And sine over cosine is tan theta. So my v squared is equal to rg tan theta. So if we square root both sides, we're going to get square root of r times g times tan theta. So let's plug and chug and see what we get. So my v is equal to then square root of r, which is 200, times g, which is 9.8, times tangent of 35 degrees. And if you work that out, I think you'll get something like 37 meters per second. Well, 37 meters per second and 175 kilometers per hour. Well, what is this in meters per second? If you work this thing out, the 175 kilometers per hour is actually 48.6 meters per second. So this is the safe speed, but the car is actually traveling at this speed. So since it's traveling faster than the safe speed, what's going to happen to this car? This car is going to want to have a tendency of drifting up the embankment because it's going faster than the safe speed. Because it wants to drift up the embankment, the friction has to act down the embankment in order to prevent that from happening. So friction has to act down the embankment because it's going faster than the safe speed, right? So you could maybe write that down. Since, right, v is faster than than 37 meters per second, right? Which is safe speed, right? The car will slide up the embankment. Therefore, right, the friction must act down the embankment, right, to prevent this from happening. Voilà. Nous avons fini. Oui. All right. Any questions? All right. So this is part A. This is part B. This is part B. So this whole thing is part B, really. Right? And then C is this part right here. Then this part A has to be finished with C being finished after C is finished. Okay? Alrighty then. Any questions? All right. I'll stop the lecture here and we can now sit back and relax and watch how the ancients thought about Earth itself, right? And how everything just almost comes to a full circle uh, from believing flat Earth back in those days to flat earthers now. All right. All right. I'll stop right here.